In this video, we're going to talk about another type of function called a rational function. So just a reminder, all polynomials are functions. They all have domain all real numbers, so from negative infinity to infinity. But there's many other type of functions. So another large class, which is what we're going to examine in this video, is rational functions. So the definition, a rational function is defined as p of x over q of x, so I've called it f of x here, where p of x and q of x are both polynomials, and the denominator one is not 0. Okay, so you have a polynomial divided by a non-zero polynomial. So let's start with the most basic rational function. So this is f of x is 1 over x. So I have polynomial 1 over polynomial x. This is one that you've probably seen before, but in case you haven't, let's think about what this looks like. And I'm going to start by doing a table of values. So I'm going to start in the middle here at 0. So if x is 0, what happens? I get 1 divided by 0, which we all know is bad. Okay, so this does not exist. So something bad happens at 0. Okay, so let's examine some other things. So maybe let's try 1. So when x is 1, f of x is 1 over 1, which is 1. Okay, so I have a point at 1, 1. What about when x is 2? Then my y value is 1/2. When x is 3, my y value is 1/3. So as x gets bigger, it seems like these y values are getting smaller and closer to 0. What if I have something that's closer to 0, like 1/2? So then I have 1 divided by 1/2. This is actually 2. So you flip the denominator and multiply. So this is going to be 2. And if I get even closer to 0, so let's say 1/3, I'm going to have 1 over 1/3. This is 3. So if I get closer and closer to 0, let's say we do 1 over 100. So it's 1 over 100. This is 100. So the y values get bigger and bigger and bigger. What about on the negative side? So if I do -1, I'm going to have 1 over -1. That's -1. -2 is going to be 1 over -2, or -1/2. So it looks like they're doing the same thing, except they're negative this time. So if I get closer to 0, so like -1/2, it's going to be 1 over -1/2. I'm going to get -2. So you can continue like this. So what's actually happening here, and we could also verify f of x is 1 over x is an odd function. So I think we talked about symmetry a bit earlier. So that means that f of -x is equal to negative f of x. And it's symmetric about the origin. So let's draw a picture. Okay, so here's x, here's y. Now the domain, maybe I should write here. So the domain for this function is that I can't have x equals 0. So in interval notation, that means I go from negative infinity to 0, but not including 0. And then I go from 0 to infinity. So something weird happens at 0 when x is 0. So I'm just going to put a little red line there. So this is when x is 0. And then we can plot our points. So at 1, we're at 1. At 2, we're at 1/2, so halfway down. At 3, okay, we're even closer. Okay, at 1/2, we were at 2, so we're going to be up here. At 1/3, we're at 3, and it just keeps getting bigger and bigger and bigger. So I'm actually getting a shape that looks like this. on that side. Now on the negative side, here I have -1 and -2, and here's -1, -2. So when I'm at -1, I'm at -1. When I'm at -2, I'm at -1/2, so closer to 0. And when I'm at -1/2, I'm at -2. Okay, and you get it's an odd function, so it should look exactly like the right-hand side, but flipped over, flipped about the origin here. So it's gonna approach here the x-axis, and then it approaches the y-axis down here. Okay, so this blue is f of x is 1/x. Okay, now we can see some special things happening. So this vertical line that I drew in red, x equals 0, this is actually what we call a vertical asymptote. Okay, and this line, this is the line y equals 0, is a horizontal asymptote for this graph. So we're going to see why we had those, and how we know if other rational functions have these things. Okay, so maybe I'll just write here. As x gets close to 0, oops. Okay, so the closer and closer to 0 on either side, the y values approached plus or minus infinity, depending on what side we came. And as x gets larger, the y values got smaller, so they approached 0. Okay, this is actually the idea of a limit that we're going to talk about in the next chapter. So, first of all, the domain for any rational function, so p of x over g of x, I think, I put g of x. Okay, this should be q, so that it matches down below, matches everything else. So let's change that to a q as well. So the domain of any rational function must exclude, so we remove any x values such that q of x is equal to 0. So we cannot divide by 0. So these are not all necessarily asymptotes, but it was in this example. So you want to be careful about that. So when does an asymptote happen? So if a function gets larger and larger in magnitude, so what that means is that the y values approach some really big number, either positive or negative. As x approaches the number k, then the line x equals k, so this is a vertical line, is a vertical asymptote. If the values of y approach a number, so k, as the x values get larger and larger, okay, so that means as x approaches plus or minus infinity, then we have a horizontal asymptote at y equals k. Okay, so the horizontal asymptotes are when x is getting bigger, and the vertical asymptotes are when the function gets bigger as we approach an x value. So let's do a couple of examples. So we want to sketch each of the following. So the first one is f of x is equal to 4x plus 2 divided by 2x plus 1. So the first thing we normally want to think about is the domain. Okay, so for the domain, we need the bottom, the denominator, to not be 0. So I want 2x minus 1 to not be 0. So that means 2x is not equal to 1, which means that x cannot be 1/2. Okay, so we want to exclude the number 1/2, but every other x value is fine. Okay, so in interval notation, that means we go from negative infinity to 1/2, and then from 1/2 to infinity. And notice I use the round brackets here because I don't want to include the value 1/2, because it's not in the domain. Now, when we're sketching, it's nice to have the intercept values. So let's do the y-intercept. So we set x equal to 0. So then y is f of 0, which is 4 times 0 plus 2 over 2 times 0 minus 1. So that's going to be 2 over negative 1, or negative 2. Okay, so we have a point, the y-intercept is at 0, negative 2. Okay, now the x-intercept is a bit harder. We want to set y equal to 0. So that means 0 is equal to 4x plus 2 over 2x minus 1. Now, knowing when a fraction is equal to 0 is actually something we're going to use quite a lot. So when you have a fraction equaling 0, it actually is 0 when the top is 0. Okay, and we need to make sure the bottom isn't 0 at that same point. But so when the top is 0, because then it wouldn't be in the domain. So you can sort of ignore the bottom and just think about the top. So if I solve this, it means that 4x is equal to negative 2, which means x is equal to negative 1/2. So my x-intercept is at negative 1/2 and 0. So now I have 2 points on my graph. Okay, now let's think about here. I'm going to put my graph over here. Okay, so let's have my axis. So now we want to think what happens as I approach the point in the domain. So that's not in the domain. So as x gets close to 1/2, the top, which is 4x plus 2, gets close to 4 times 1/2 plus 2, so that's 4. Whereas the bottom gets close to 0. Okay, when I divide 4, something that's close to 4, by something that's close to 0, this means that the y values are approaching some sort of infinity. Okay, I don't know which one, but they're getting really large. If you do in your calculator 4 divided by a number that's really, really close to 0, so let's say like 0.00001, okay, you're going to get a really big number. So this is going to, the y values are getting really big. What that tells us is that x equals 1/2 is a vertical asymptote. Okay, so here's 1, 2. So at 1/2, we're going to have a vertical asymptote. Now, as x gets large, I'm running out of room here, so I'm going to use shorthand. As x goes to plus or minus infinity, so it gets really big, the top, 4x plus 2, is going to approach 4x. So the plus 2 isn't really going to matter. And the 2x minus 1 is going to approach 2x. So it doesn't really matter either, the negative 1. Because if x is really big, then 2x is even bigger. So minus 1, it doesn't really matter. So that means that if I divide these things, I'm going to approach 4 over 2, which is actually 2. What this tells me is that there's a horizontal asymptote at y equals 2. Okay, so I want to put that on here as well. Now, horizontal asymptotes you can actually cross, but you don't always. So we're going to plot our points. So 0 is at negative 2, so that's down here. And at negative 1/2, we're at 0, so somewhere around there. And the shape is going to be similar to the shape for 1 over x. So if you're not comfortable, I just want to do a brief sketch here, and I'm kind of out of room to write more information. But the shape is going to look similar to what it did for 1 over x. Okay, but if you should probably do more points, okay, because we don't have very many here. But it's going to look something like that. For the horizontal and vertical asymptotes, once we get our hands on some limits, we're going to have a ways to write this a bit better so that we can sort of be a bit more succinct with it all. But this is what our graph would look like, something like that. So let's try one more. This one is actually a bit easier. So first I'm going to do is simplify a bit, but not fully. Let's just make sure we don't run into that. So I want to factor x squared minus 2x minus 3. So I want two numbers that multiply to give negative 3 and add to give negative 2. So that's going to be negative 3, positive 1. So this is going to factor as x minus 3 times x plus 1 over x plus 1. Now before we do any simplifying, we should compute the domain. So we need x plus 1 to not be 0, which means that x cannot be negative 1. Okay, so that's our domain. But because of this factored, we could actually cancel this, and it would be equal to negative 3. Now this is true as long as x is not negative 1. So if you have 0 over 0, you can't actually cancel that. But if it's a number over a number, then it's 1. So everywhere that x is not negative 1, our function, g of x, looks like the function x minus 3, which is a lot easier to sketch. At the point x equals negative 1, it's not in the domain. Okay, so really our function equals x minus 3, except at that point. So maybe I should write that down. So the graph of g of x is the same as that for y equals x minus 3, except when x equals negative 1. Okay, where g of x is undefined, because we have to compute the domain before we do any simplifying. So what this means is that our function actually looks like a line. So here's the x, here's the y. So I'm going to start by drawing the line x equals negative 3. So hopefully you kind of have an idea what this looks like. Okay, so it's a line with y-intercept negative 3 and slope of 1, which we're going to talk about slope more later on. Okay, so that's not very good. But okay, so it's a line that looks like this, and then in this direction it goes like this. But there's a problem when x is negative 1. Okay, so everywhere else it looks like this. And even if you're at, so when x is, say, negative 0.9, okay, really close to negative 1, the y value is g of negative 0.9. We can use the simplified version because it's not negative 1. So this is negative 0.9 minus 3. So it's negative 3.9. Okay, you'll get closer and closer and closer to where this point should be, which is negative 4. So what happens is you just get a hole in the graph. Okay, so I'm going to write here, this is a hole at negative 1, negative 4. And this is the point that should be on the graph of x minus 3. Okay, so it's the point at negative 1, wherever it should be. That it's just been removed from the graph. So this always happens when you can simplify like this. Okay, so if you can simplify and remove sort of the problem, then you don't get a vertical asymptote, you just get a hole. Okay, so that's a very brief